Hello class, this is CSE 5250, Section 1, Week 8, Spring 2023. Hopefully by now you've submitted your programming assignment 2, but just in case you haven't, keep in mind that I have a 1 week window in which you can submit assignments past the due date, unless you have something important or pressing came up, extenuating circumstances that resulted in you having to submit it even later than the due date. So if you end up submitting your programming assignment 2 late due to say debugging issues, and it's within the 1 week, within 1 week of the due date, I will still take your programming assignment. So, what are we doing now? Well, I will say right now that this video might be on the shorter side, partly because, well, look at the date. St. Patrick's Day. I didn't even realize it was St. Patrick's Day until I didn't even realize that was the day until I went out and realized, oh, there's a St. Patrick's Day band over in the such and such area. So yeah, didn't even realize that. So maybe you might be watching this. Maybe you might be delayed in watching this. I am definitely delayed in recording this, but don't worry, this is gonna be more on the short side because we're just talking about more about how we can do data collection on our program here. And next week, hopefully by next week, I want to start talking about at least starting an introduction to MPI, because that's a message passing interface, which is used for, well, you know how we can have processes think that they have the computer to themselves. When two processes talk to one another, if they need to talk to one another, one way is to have shared memory. But if they're especially on different computers, then we need to send messages between them. So anyway, here is our current assignment. Benchmarking for the sieve of Eratosthenes. Ultimately, we're trying to answer the question, is it worth parallelizing this program? Because the thing is, some problems in computer science just take way too much time to solve, but some of them can be broken up and spread among multiple threads or processes, thereby making the program run in less time than if we only had one core on it on which the program can run. In other words, does this program run any faster? And if so, does this program run much faster if parallelized? And if so, by how much? And how many cores do we need to make it run faster? Anyway, right now for this video, I'm just going to talk about a little bit on the data collection side. So this is a different sieve of Eratosthenes that I actually wrote when I first took parallel programming. So I have it set up a little bit differently from the sieve that I was showing you. That sieve was a little bit more basic. It's a lot more cut back, and that's because I wanted to show you what the algorithm looked like as computer code, as C++ code, I should say. And much of the code was actually just a parallel for loop that was itself part of another for loop. Of course, there was another parallel for loop, but that was because I wanted an array containing all of the numbers that I was trying to search through. Excuse me. There is more than one way of programming this type of Eratosthenes. I'll give you at least one other way, and it's this. Instead of having a vector of integer values, we could instead have a vector of Boolean values. So when I do this, I would basically have an array, a vector of size search max that's full of true. I would basically infer what the number was supposed to be just by using the index alone. So just I and j here. If it was, say, if I or j was like the number 73, then that's enough to infer that the number it's referring to is the number 74. Because indices start at 0, we have to offset everything by 1 in that regard. Anyway, I'm not using bools, I'm instead using ints. Though you may have noticed that I had it set to long previously. Don't worry about that. That was in case we were trying to see whether this would work for values larger than 2 billion. Anyway, let's look at data collection. Of course, we can just run this thing over and over and over again. And that is one way of collecting data, though it'd be super duper tiring. We can add some extra code that basically writes all of this data to an output file, and that would work too. But eventually we want to take all of these numbers and basically find an average. But there would be 16 sets of data points for which we have to do this process. So obviously it would be non-ideal to have everything in the same output file. So this output file would have to be, you would need separate output files for every combination of, for the sake of organization, you would need to have separate output files for every possible combination of search max and thread count. I have been starting with these 16 values, but remember, you can go beyond those values if you want to. Even if it's just for the sake of pushing your computer to its limits, which you could do. But keep in mind, we have finite amount of time for this course, so. How would we set up this program for automatic data collection? By that I mean, we want this thing to be able to, we want to set up a system where we can just tell the program, hey, I want to run this program with this many threads and for a search max of such and such. This many threads, just such and such search max. I'm going to show you one way to do this. In fact, this is what I wrote for when I took the course. This is what I wrote when I first took the course itself. So, int main, and we want in the parentheses, int argc, comma, character, star, argv, square brackets. So, that's the first thing you do. So it's basically, we're setting up a program that if we're to run it in the command prompt, it can take in parameters. We want to pass in 2 parameters So ARGC would have to end up being 3. The first parameter would end up being search max. The second parameter would end up being thread count. Of course, I have it set up so it will default to some default values. But if those two numbers are passed in, it will reassign these two values, search max and thread count, to whatever values I want. And if I didn't have them, it's okay. It'll just run with these values instead. I have this thing to take in an optional third parameter, but keep in mind, this is because this is how I wrote it. It's because I wanted the ability to do data collection be optional. I can say, yes, write it to a file, or no, don't write it to a file just yet. I want to see the results for myself before I start writing it to a file. Anyway, the gist of this is basically having, if I have ARGC equals 3, which means I'm passing in 2 arguments, then I want those 2 arguments to correspond to search max and thread count. A to I ARGV1, A to I ARGV2, because, well, these are ints. So search max becomes whatever the first argument was, thread count becomes whatever the second argument was. What would this look like if I'm to execute it? Well, let's go to open folder in File Explorer. I tried doing this once and Windows Explorer basically crashed on me, so I had to restart that and restart the recording. So that was fun. And by that I mean not fun. Okay, so that's the main CPP file. I have these things here. That's not it. Or is it? I have to go back up one level and go to this debug folder, and look at that. Basically, I've ran this several times already, but I'm just gonna do the basics like this. This is gonna be specific to a Windows system. This is building off of using standard Chrono. And this is one way of doing data collection. I talked to a student who basically did data collection that was not too dissimilar to what I did. So I'm just gonna show that to you right now. CMD in the address bar will open a command prompt where I'm at right now. If I do cpp underscore EPP civveritasanies.exe, I run the program, it didn't record anything. That's because it didn't record anything because I only passed in one thing, and that was the name of the program itself. I would need 3 parameters, and by that I mean it's actually going to be 2 parameters because the first one's actually going to be the name of the program. So if I'm to do the same thing again, what would it look like? CLS to clear all of that. Up button to get this again. Oh yeah, how do you get to this stream? Well, let me show it to you again. And I realize now I have to show it to you again because my webcam must have probably obscured it. Solution Explorer, click here. Open folder in File Explorer. Go back one level. Yeah, go back one folder. And then you may have noticed a debug folder in here. That's not the debug folder we want. We want to go up one level to the same level that contains, if you're developing this using Visual Studio, you want to be at the same level as your .sln folder. You want to go to that debug folder, and you'll find, among other things, the compiled executable. That's what the one we want. So if I run it, I can double click it to run it, but it'll just close immediately. And that's not what I want either. So again, we want to open up command prompt. I'll show it to you again. Close that. Go to the address bar, type in cmd, and then we can let's run the command. And again. And again. But nothing's happening because I programmed this program. I set up the program so it'll only do data collection if I gave it a parameter that said, yes, write this to a file. So, so instead of just pasting this in, what if I did this? And remember, the parameters were, the first parameter should be, I'll just move my webcam to the left instead. The first parameter is the search max. So, let's do a search max of 1 million, and then 1 thread. It's taking a while because printing to the screen takes some time. Should be there though. There it is. That took a while, so maybe it reported 845 microseconds to... Hold on. No. If I can find the right one, because I reported 90,000 microseconds to look for primes up to 1 million using 1 thread. And yeah, that is what you could call fast. Though the writing through the screen took way more time than just finding the numbers, so okay, this is why I have it. That's why I have this example program set. That's why I have this program set up. So I have it writing the results to a file. So if I added an extra 1 as a parameter, the code will basically say, "Ah, you're writing it to a file." And so there's going to be an extra section of code that will either write to a file or print out the results. And this is it here. I'm basically writing to a file, and the file name is going to be based on the search max and the thread count that I entered as parameters. So basically, I've automated the whole process of data collection. But of course, you still have to type the whole thing over and over again, which again isn't ideal. And that's why I did this. I wrote a batch file. Maybe you have too. Maybe you've written one of these before, but if you want to go this route of data collection, and you want this as an example, this is what you write for /l %% in 1, 1, 100 do set of Eratosthenes executable, and then the parameters are 1000, 1, 1. And then I repeat the same process for every possible thread count, and then I do the same process again for every possible search max that I wanted to search for. And this alone is this will basically do everything in one step, except for the part where you have to populate a table, because it's just going to, this program basically spits out everything as several text files. So eventually, what you would need to do is take all the numbers, find the averages for each of these files, and then with that table, we can populate it. With that data, we can populate our table, and then we can finally answer the questions: where is the sweet spot for thread count, and where is the sweet spot for workload size? Or alternatively, how many threads? At what point does the addition of more threads results in diminishing returns, and at what point does it become beneficial to run the sieve in parallel? So those are the questions we're ultimately going to answer, and just to make sure that this thing really is printing out numbers, what I'm going to do is I'm going to run this sieve for a really big number and see how long it finishes. So maybe, what is that, 100 million? Yeah. And I'm going to use as many threads as my computer can execute at once. So that's 16 threads. Let's see what happens. And just like that, I can tell that this is new because it has a timestamp telling me when the file was last modified. So this is the file that it made for me. And it reports that it took about 4.5 seconds to run. So yeah, that's the basics of how we can automate the entire process of getting the data we need to populate the table. This is specific to Windows, by the way. I would not know off the top of my... To be honest, I would not know how it would work on a Linux system, but I suspect it wouldn't be too far off. So yeah, that's data collection. So maybe now we can just do a little experimentation with the Sieve of Eratosthenes, such as does it make an impact whether we parallelize the outer for loop or the inner for loop? If it does, and you find that parallelizing a different loop worked faster, then when you do your data collection, you must have the same code being executed for everything. This is just more for experimentation, as I said. So instead of parallelizing the we're parallelizing the outer for loop instead of the inner for loop. Does this make any impact to the execution time? Let's see if it does. And oh, by the way, turns out you can add apostrophes as separators, so this way I know for sure that this is the number 100 million. I'm going to run this program for searching for prime numbers up to 100 million. I'm going to set the number of threads to 16. I'm gonna see whether this works. I'm gonna see whether this works, and I'm gonna see what kinds of times I get as a result. Open in File Explorers because I have an output file here. This one's gonna tell me this is just gonna pretend as a sentence, and that's okay. If you want to be able to copy this to say Excel, we just want the numbers themselves. So basically this video is tips and tricks on how to automate the process of collecting data to fill out our table. And then it's a little bit more on the side of, hey, let's experiment for a little bit and see what kind of times we get based on whether we parallelize the inner for loop or outer for loop. Let's see what happens. So if I run this, And now the only thing I'm changing in this experiment is what for loop am I parallelizing? This is taking a while. Okay, found prime numbers up to 100 million in 27 seconds, and that's if we parallelize the outer for loop. So keep this number in mind. I will say right now, I think I found a bug with my program, or rather, an undesired behavior. I think it's overriding the previous data. So we'll just have to keep that number in the back of our heads. The previous experiment, the experiment of running it with the for loop, outer for loop being parallel, gave us a 27-second execution time. So I'll just make a copy of the file. And now this is more for experimentation, if anything. So we're gonna see what happens if we parallelize the inner for loop. What happens now? Will it take 27 seconds, or will it take less time, or more time, or will it take the same amount of time? So and we got an answer. It took 10 seconds less to run it this way with the inner for loop parallelized than if we're to run it with the outer for loop parallelized. So we ended up answering one question, and that is basically which for loop do we have parallelized? And if you think about it, it kind of makes sense too. If you think about it, it kind of makes sense, because the process of crossing out multiples of prime numbers, if we don't care about whether the number was prime or not, then we're just crossing out multiples of every number. I don't know if that makes sense, but actually no. The way I said it means if we're crossing out multiples of every number, then we'd end up crossing out all the numbers. So maybe for the sake of consistency, let's just have it so the inner for loop is parallelized, not the outer one. So with that in mind, hopefully I've given you some ideas on how to parallelize the for loop. I could give you instructions on how to install MPI now. I could do that, but maybe I can save that for next week. Again, for this week, we're just gonna focus more on data collection, how to get the data needed to populate our table. And with that, that's gonna be it for this video. As I said, it's gonna be a short one because we're just basically, as I said, right now we're just doing our midterm assignment, which is data collection. One other assignment that you have to do though is, of course, it's a short answer question, which is, as a sort of prediction for your midterm assignment, how many CPU cores do you think is ideal? I talked a little bit about Amdahl's law last week and a little bit in class as well. So this is your question. it's a little shrunken. But if I copy paste that into Paint.net and zoom in, you should be able to see the question I'm asking you. So, as a sort of prediction for your midterm assignment, and I have this question due today as well. So hopefully by the time you watch this, both your short answer question for this and your programming assignment 2 will have been submitted by then. So yeah. How many CPU cores do you think is ideal? And the hint for this is think about Amdahl's law. Right, so that's going to be it for this video. It's a little bit on the short side, and that's because we're just focusing more on data collection now. Anyway, that's going to be it. If you have any questions, feel free to let me know via email or Canvas message, and that's going to be it. If you have any other questions that involve debugging, you can always just come in for the Monday class where we can just talk about debugging things together. Right, that's going to be it. See you next week.